Hey there, this is Kyle Kimbrell with another episode in the Owens Recovery Science podcast. I think you'll really like today's episode. It's a different topic, something we haven't really tackled at all, something that, quite honestly, we often discourage. We're going to talk, well, should you maybe lift heavy weights with BFR? And to help us tackle this, we have a researcher from the University of Alabama. His name is Lee Winchester. And they have published one paper on their findings, and then they have a number of other different trials in the works. And so this is a fun conversation that we had with Lee. We're not holding the fact that he's at Roll Tide U against him really, but I hope you guys will enjoy this. And before we get to that episode, I have a teaser for you. I'm going to tell you that there's something big that we're about to do, and you're going to want to pay attention to our emails and our social media accounts, because we'll announce this and it'll be very prominent along those means of communication that we have. But I promise you this, if you miss it, you're not going to be happy. So please just stay tuned. We're working out all of the little details, but this is going to happen, and it's a very big deal. So, the vast majority of you that listen to this podcast are going to want to participate, I believe. So, without further ado, how's that for a teaser, by the way? That was pretty good, huh? Are you wondering now? I know those of you that took my course, you're thinking I'm about to see a picture of where the tourniquet is supposed to go. And no, it's much more enjoyable surprise than that. So at any rate, let's kick this over to Johnny and myself and Lee.
This is the Owens Recovery Science Podcast, hosted by physical therapist Johnny Owens.
So Kyle, our guest today, I think he wins like coolest name award because he sounds like he should be in a West Texas movie. Sheriff Lee Winchester from Lubbock, Texas. So today we've got Lee Winchester on.
Hey, Johnny, hang on. But my dog's name is Winchester, so there is that. But I named it because it's cool. I was like, I'm going to buy a gun or a dog, and I bought a dog, so I named it Winchester. So
that's all, man. I get stories about my name all the time. It's either people who are either from the UK, generally because of Winchester and stuff like that, fans of firearms, or somebody who watches Supernatural. And somebody always has a story with my last name. Like, hey, can you do that? Yeah. It's always something. It's great, man. I'm like, I have like the most traditional British last name known to man, but.
Oh man, West Texas Sheriff Lee Winchester. I like it, man.
So, I get it, man. I'm game.
So Lee's a friend of mine. We met, I think, around like 5 years ago at a course I did in Louisville. And so he was at Western Kentucky at the time. Now he decided he wanted to be at a winning football program. So now he's at the University of Alabama, who we work a whole lot with in their athletic department. I've had the honor of sneaking into, he was gone. They took me into Saban's office so I could see his 9 million rings sitting on his table there, which was pretty freaking crazy. But
man,
Lee's
I don't
in
even have
University
privileges like that, Johnny.
I know. They told me like, do not put this out on social. I probably wasn't even supposed to talk about it.
We'll edit this out. No.
Yeah.
It's like a you don't talk about Fight Club type of thing.
But he got his PhD at the University of Louisville, School of Medicine and Physiology and Biophysics in 2015. Like I said, now he's at the University of Alabama. He's a physiologist out there. He's doing some really cool stuff. And when we talked at the course, he was kind of really doing deep dives on muscle damage and what it does and how BFR might also kind of upregulate hypertrophy. So I was like, man, I really hope this guy, takes this and starts doing some BFR research. And he has. He has an interesting paper that's come out looking at high load training with BFR, which I think is kind of one of the things you really look at quite a bit. Also looks at what training in the cold does with exercise, not specifically with BFR, but training out in the cold. So kind of looking at some really cool things there. So Lee, welcome on, man.
Thanks, man. I'm happy to be here.
Yeah. So give us a little bit of your background. You grew up in a cornfield, and then kind of just slowly moved down to the South, but what got you into physiology, and also what got you into thinking about doing BFR for research?
I'm from a small town in Indiana originally. It's a little town called Cedar Grove that nobody's ever heard of. You Google it if you Google it, Wikipedia will tell you it's 156 people, and that's accurate.
Wow.
I grew up in the middle of nowhere. So yeah, I joke with all my students and stuff that I was raised by wolves, even though, there's no wolves in Indiana, but hey, so I grew up there, went to Purdue for my undergraduate in exercise science. And back then they didn't really know what to name it or where to put it. So they just called it health and kinesiology. And so, which at the time was their exercise science program. And, so my senior year there, I took advanced exercise physiology, and I'm not going to lie, my performance in my first few years of undergrad, let's just say going from a town of 156 people to a college of about 50,000 was a bit of a shock to me in a good way. And so I had a little too much fun my first couple of years. But after that, my senior year, I took this class, and I had a professor, his name was Mike Flynn, who just really inspired me. He was a great instructor. And he started talking about toll-like receptors, and I was like, I don't even know what that is. So I started Googling it and looking into it. I don't know if it was Google at the time. It might have been Yahoo, but started looking at that, and it just really got me interested in it. So I pursued a master's in exercise phys at University of Louisville, and realized that more than anything, I really loved the molecular aspect of it. And so I wound up doing my PhD in physiology and biophysics through the medical school there. And from that, it's just kind of my passion. I found, it's no offense to the basic science physiologists out there, but I just found through that program versus some of the exercise sciences, personality-wise, I tended to get along a little bit better with the exercise science crowd, just a little more laid back, I feel. And so that's why I came back to exercise science, and my research kind of blends those two backgrounds. So it's just what really drove my passion for it. But I actually started doing BFR. I had an undergrad at West Kentucky who actually came to me because he used it in a PT clinic and had stated, this thing's really cool. Do you know how it works? And so I was just kind of speculating. I didn't know anything about it, to be completely honest. And this was in about 2016, early 2016 in the spring. And so that's when I started really diving into the literature and realized, wow, this is pretty cool. It makes sense that this works because of the hypoxia and metabolic stress that you're causing as a result of not supplying adequate blood flow to the muscle tissue, right? And so it just, again, that whole basic science nerd side of me just completely took over, and that's what drove my interest in it. And so that's what kind of led me to BFR research. And then, here, compliments to you, man. I was reading up, and it seems like Owens recovery science was the way to go. And that's what I do my research on now, is using your cuff systems. So
yeah, awesome, man. Yeah, well, it's cool. And you're going after something. We get a lot of questions, especially from the teams, is how would we work this in, not from a clinical side, although what you're looking at really applies to that as well, but how would you work this in to maybe maximize your performance? So strength changes, maybe muscle changes from a hypertrophy standpoint. And so you've been looking at combining and looking at this with heavy loads. You want to kind of touch on that and why you wanted to go down that crazy route?
Yeah, absolutely. So number one, the one factor that kind of drove me in that direction initially was the fact that I was like, not many people have touched it. It's one of those areas where it's untouched for the large part. And all things considered, I came to Alabama. I was in my exercise science program. I'm kind of the first person to really do a lot of like cell-based research or anything like that, or blood draws and looking at protein changes and things like that. So I was like, I knew I wasn't going to be able to do a whole lot of stuff that could dive deeper into the mechanistic side of low intensity with BFR. And so I was like, well, let's go ahead and start to kind of more of a superficial level, start exploring some of these avenues with high intensity, just because it was an easier access point. But, with low intensity BFR, almost every study conducted is suggesting that, hey, the mechanisms are in place. You cause hypertrophy, almost similar to what you see, if not completely similar to what you see with higher heavy loads, causing hypertrophy in the chronic phase responses. So as a result, the mechanisms are there that even without muscle damage and without that mechanical transduction that you see with those heavy loads, right? that's how the majority of those heavy loads tend to cause hypertrophy, is through mechanical transduction, integrin receptors being stimulated, causing cell signaling pathways that result in hypertrophy. Versus with BFR, at low loads, you're still not causing that. There's no reason to believe, and there's not a lot of data out there supporting the idea that muscular damage is increased to any significant point. There's no reason why you would have increased mechanotransduction. So by power of elimination, that leads to metabolic stress and hypoxia. And so part of my line of thought with going towards this route, towards this high intensity, is there's a plethora of different cell signaling pathways that are all activated. A lot of those, as I know you discussed in your presentation back in Louisville, 5 years ago, talking about mTOR signaling and how you activate mTOR pathways, which ultimately activates transcriptional activator molecules to promote transcription and upregulation of protein synthesis. But there's other pathways that are involved too when and when you're talking about heavy load resistance training and you're working largely through mechanical transduction, and albeit, yes, there is some metabolic stress that's of course going to happen from the activation of, type 2 muscle fibers, things like that. You're still going to see, from what the literature is suggesting, an additive effect when you add BFR to that high intensity load, right? So you're initiating mechanical transduction, you're causing supraphysiological hypoxia and metabolic stress beyond what you would typically see. At least that's what most basic so far literature suggests. And that's pretty much my thought process behind this as well. If you're activating these additional pathways, enhance protein synthesis even more, that could potentially lead to kind of a, synergistic response to even further induce hypertrophy. And that's kind of what spawned all this, all my current research.
So early on, there was a little bit of a push when we were looking at BFR, and some of the exercise phys side was saying, well, if it looks like there's no muscle damage, so how can this work? Muscle damage is required to make this adaptation to muscle. And we've had kind of probably more than we should recently, a lot of muscle damage talk back and forth on this podcast, because we put out a paper in Frontiers of Physiology, and then some authors came back and said, we didn't address the muscle damage piece right. We came back to them and said, yes, we did, and yada, yada. You're just looking at something like creatine kinase. So can you get into why muscle damage is important from a heavy lifting perspective, and then you in the lab, how you would measure those type of changes?
Absolutely. So muscle damage, man, that's so heavily debated. It's one of those things where all the original research, right? You see muscle damage post-resistance training, you see enhanced protein synthesis, all these transcriptional regulators like P70S6 kinase, heavily upregulated, right? Suggesting that you have heightened protein synthesis. You see, there have been so many studies that directly assayed for protein turnover and amino acid integration into proteins and peptide structures through radio labeling or whatever. And it's obvious, right? Protein synthesis is enhanced dramatically with exercise-induced muscular damage, right? So EIMD, it's unquestionable. Now, there's been so much speculation, I know, over these past few years that is that a good thing or is it a bad thing? Because, right, you see a lot of protein turnover and a lot of protein degradation that occurs along with that muscle damage. So is it actually causing hypertrophy? I've seen a lot of stuff recently, and again, this is just my opinion, where it's showing that, no, that might not be the case. But honestly, I'm personally not convinced yet. I see this muscle damage and see, okay, a lot of the research is showing that, yes, you see increased protein synthesis, but you see protein degradation along with it. However, there have also been longitudinal studies, not necessarily, I haven't done them personally, where you will see this initiation of protein synthesis from muscle damage. And then as a result, all these adaptations start occurring, right? So enhanced protein synthesis, the long run, that eventually, yes, does dwindle away as muscle damage tends to dwindle away, and they're still hypertrophying. But along with that, I can't even remember who the author was. It was only one paper I found, and I read it, truth be told, about 2-3 months ago, and I thought it was really neat. And since then, I haven't touched it because of dissertation defenses I've been working on and stuff. But it was kind of neat where it was also showing that along with that, if you don't have that initial damage, hypertrophy is not as profound. And as a result, I'm not saying it's the end all be all. I don't think that it is absolutely required for muscle growth, but I don't think it's a bad thing either. I think it's definitely something that helps induce adaptation in the long run that ultimately solidifies muscle structure, right? Increasing muscular, rigidity to help make it more structurally sound, to resist heavy loads. And I don't think that's a bad thing at all. But with these other mechanisms in play, I don't really foresee a reason, like you were saying, why BFR would really enhance muscular damage or anything of that nature. Because I remember that was something you had kind of talked to me about, which is, right, does BFR do it? So far, my research that I've done, now granted, my study that I have in JSCR that came out last year, like towards the end of last year, I think in like December or something like that, we did intermittent blood flow occlusion. So we were doing it during the set. And part of that was just safety, right? Part of that was just the fact that we were trying to be cautious. We're doing high intensity, right? We're already causing muscle damage. There's not a lot of data out there prior to when we were conducting this study suggesting, hey, this is even remotely something you should do. So we were trying to minimize the risk. And since then, I've been baby stepping it and building on that original study that I kind of did, to keep going basically more and more rigorous to mimic what you would actually see in a weight training facility, right? If you're an elite athlete, are you going to get benefit of this from this? So far, results are pretty interesting. That's what my PhD student, who literally just defended this past Monday, he did his entire project on that, and the protocol was absolutely brutal.
I don't know how you get people through it, man. 80% limb occlusion, 75% 1RM. I mean, what the hell?
It's intense. Well, I'll be honest. I'm in nowhere near as good shape as I used to be because kids, dad bod, and all that stuff. But I practiced it myself, and I'm not gonna lie, it's not fun, but doable, right? It's mind over matter in that case, right? You just keep going. You know that it's for the research or whatever. And realistically, this protocol was a little more advanced than what you would probably naturally do in the gym anyhow, because each set was still failure. So that in and of itself is a little more intense than what you're naturally going to do if you're being honest, right? Like I don't go into the gym, and when I'm doing squats, I don't go until I basically drop to the floor for every single set. So some of the research from these, some of the results from these studies is pretty neat, and it's definitely indicating that I should probably go down this route and do a little more research on it. But this JSCR study, the intermittent blood flow occlusion, it's only occlusion during the actual set. I released it in between for some metabolic clearance and things like that. Very limited pre-post analyses, again, because I wasn't really 100% comfortable with it yet. I didn't want to put anybody under too much pressure and then get sued or something like that. Well, it would have been the university, but nonetheless, I didn't want that either, right? So I was kind of taking it easy on them at first, and did some pre and post blood draws. And with that, so that protocol was 3 sets of squats at 75% of your 1RM, right? Pretty intense. I mean, pretty standardized protocol. Like if you were in the gym, that's kind of what you would naturally do anyhow. And I did.
Let's break it down too. So it's an acute trial. So
yes.
Right. So they came in, did either 75% free flow or 75% with BFR on. Right.
Yes.
Right. So it wasn't a training trial. So and what was your going into it? What were your thoughts, and then what were you wanting to measure and see from this?
So the main things I wanted to measure and see was, okay, number one, are we causing more muscular damage? That's something I wanted to see. And so for me, creatine kinase, just because of, and again, I could be wrong on the, kinetics with this a little bit, but it seems like it kind of has some rapid turnover. It's not the most reliable necessarily measure of muscular damage, although it's used all the time. I'm never going to knock it, right? I've seen it in labs that I've worked with, and I think it's definitely a good indicator. But I tend to go with myoglobin. It populates a little bit faster. You tend to see it upregulate within an hour inside of the plasma. So I was looking at changes in myoglobin status in the actual plasma pre and post exercise. And I was using that as a muscle damage indicator. And then I was using interleukin 6 as kind of a upregulatory mechanism, indicating, obviously I was limited on supplies and, equipment to actually do detailed analyses, but I could run a assay plate, right? So I ran IL-6, interleukin-6, to see, okay, what's happening with this very prominent pro or anti-inflammatory cytokine, depending on the scenario, that is known for inducing a lot of hypertrophic responses and satellite cell mobilization.
Right.
So one of the things that I saw, in both of those, there was a little bit of trend for BFR to be higher with IL-6 and myoglobin than what we saw with control. That being said, it wasn't statistically significant. So as far as things are considered, right, it wasn't different. They were both upregulated over baseline, right, over that, pre-measure. So as we expected, right, we don't expect high levels of inflammatory cytokine release or high levels of myoglobin in the blood if you're just relaxing. And so those were both upregulated, which does tell me, right, if BFR is causing muscle damage, it's to a very mild extent. I guess
these were trained people, right, Lee? They weren't.
Yes.
So this wasn't like an untrained population, initial exposure kind of thing. These people had at least some of the repeated bouts effect kind of on board. And
absolutely. So we made sure that they were resistance trained, if I recall. And again, this study was a little bit older, and I just kind of got around to publishing a little late. But if I recall, it was about 6 months of resistance training experience to make sure that this wasn't going to be a massive training effect, right? From from trial 1 to trial 2. So also just to account for that, we did randomize it. So it was a counterbalance. It was a counterbalance design where some people went BFR first, then control. Some people went control first, then BFR. So we tried to ensure that there was no major training effect, at least observed in the data with that, to control for that.
I think it's interesting. I mean, to my knowledge, and you would be more knowledgeable of this, but I don't think it's terribly common to see a muscle damage paper that's on like a trained individual. I think sometimes we might even conjecture that, well, how much damage is occurring when you're resistance training after you've been training for a while, So I thought that was kind of interesting too. Just really kind of an affirmation that you are still disrupting that myofiber, and this is a mechanism for hypertrophy even later on in kind of a training scenario. So.
Yeah, absolutely. And I mean, a lot of the research, like I said, does show that muscle damage does decline over time, right, as you train, unless you have just some incredibly horrific load that you're exposing your body to. So yeah, that does kind of confirm it, right? It was nowhere near as profound of an increase as we probably would have seen if we took a bunch of people that have never worked out in their life and said, hey, we're going to expose you to 3 sets, 10 reps, 10 to 12 reps of squats. Can't remember. I think it was 12 reps of squats. And, they probably would have had a significant increase in muscle damage as a result, but then they also probably would have, passed out, had all kinds of issues. Frankly, they're not used to it. So.
Then that lawsuit would have come.
Yes, exactly. So yeah, we try to get control for those things to make sure and maintain participant safety while doing all that.
You did see a trend, and we would expect this in fatigue, or significance in fatigue, if you put the cuffs on, right?
Yes.
Right.
And that makes sense, right? Whenever there's so many mechanisms through that's causing fatigue, right? You're talking about a reduction in ATP production. Granted, when you're lifting, it's largely going to be anaerobic, right? You have phosphocreatine breakdown, all that. But when you have the inability to clear lactic acid, and you are, with the Delphi cuffs, you're pretty much shutting down venous return from the legs. You're drastically reducing arterial flow into the legs, delivering fresh blood, things like that. That is not prominent, does not have high concentrations of lactate or hydrogen ion associated with lactate in it. That hydrogen ion accumulation has been shown to shut down group 3 and 4 afferents that stimulate contraction. All these things, like these are definitely factors that cause decreased muscular activation. You downregulate phosphofructokinase. You downregulate all kinds of metabolic enzyme activities that are going to drastically reduce your ability to produce force and contraction. So to me, it makes sense, right?
Right.
Kind of expected at this point that, especially if we're doing high intensity, you're going to see faster fatigue. And that's been confirmed even further with the research that we've been doing lately. So yeah. Well,
then we've always said that BFR is a way to get you to fatigue quick.
Yes.
Low load, you can see some changes if you do free throw low load, but it takes lots of reps. We can get a cuff on you and you'll fatigue quickly. So What's your takeaway from the paper overall?
So my takeaway is that BFR, and from that initial paper, is that BFR is going to induce fatigue more rapidly. I can't have any conclusions, from this paper saying that, hey, BFR with high intensity resistance exercise, I cannot conclude, succinctly from it that it is causing any kind of additional benefit. I can't come to that conclusion just based on the limitations of the measures. However, that being said, you did fatigue more rapidly. Pain, it's also not pleasant. I will.
Yeah.
I have tried it. It is not pleasant. It does burn a little bit. But actually, that concept is what also spawned another dissertation project from one of my doc students that they did, looking at different limb occlusion pressures that we could use in the lower limbs as opposed to that 80%. In which case it's, just between, here it's starting to look like 60% is doing very similar things in the lower limbs as 80%. So allowing just a little bit more blood flow, don't have quite the pressure, don't have quite that tourniquet feeling, it might alleviate a little bit of that pain response. That's kind of our next step where we're going with the next project. So that's going to be a fun experience. We'll see how
with heavy load or low load?
Heavy load. I'm pretty sold based on our recent research. And again, if you want me to, I can go ahead and talk about it a little bit, because
sure.
Point where the manuscripts are being written up, like if somebody beats me to the punch when I already have the manuscripts in prep, like that means I'm doing something wrong, right? Yeah. That being said, so this one study we just did, it's basically we're taking similar type of protocol as what I did, except for it's 4 sets of barbell back squats at 75% of your 1 RM with every single set until muscular fatigue, right? And so with that, we expected there to be a discrepancy in total load, like total work done or completed as a result of the BFR. So we were comparing BFR and control again. With this, we had occlusion for the first and second sets, including the rest periods. And then during the rest period after the second set, we deflated. And that's kind of based on, we were timing it out, doing some pilot testing, about 8 minutes, give or take, right? Mm-hmm. For that first 2 sets, we occluded it about about a minute before the first set to cause some occlusion. They did the first set, left it inflated, did the second set, and then I think it was 30 seconds after the second set, we deflated it, right? And that kind of wound up being about that 8-minute mark that, generally speaking, is referenced in the Owens Recovery Science Manual and things like that, right? For that limb occlusion, occlusion time, right? But then we followed up and re-occluded right before 30 seconds before the third set, and then left it occluded all the way through the 1 minute post the fourth set. So you have a very long occlusion during this, because the research is out there. It does appear that there is a little bit of metabolite accumulation during the set, but it looks like there's more metabolite accumulation in during the rest period, right? Where you really cause a much more profound effect. Muscles trying to recover can't. And so that's why we're like, okay, well, combine them, do everything, leave it. It's at 8 minutes, right? Maximize this response. As I'm sure you can imagine, performance just tanked. Just absolutely tanked with BFR. In fact, it was about half. The performance was cut in pretty much 50%. So that was as expected, right? But you saw what was kind of neat with control. We kept seeing this gradual decline in number of reps performed, though none of them were actually statistically different from one another. Right. So it was a general trend, but they weren't statistically different. It just was not a big enough drop from the first set to the fourth set as far as how many repetitions they could produce. However, with BFR, it was kind of neat where first set you saw it pretty much match control. But then second set, it was about a third of the number of reps as you originally had. Like it went from about 12 reps down to about 4. And then you deflated the cuffs. And next thing you know, there was no significant differences during that third set between BFR and control, telling us, right, you're not hampering the muscle tissue as far as the actual structural integrity of it. You're not doing anything like that that's going to prevent a force or like reduce force of contraction, things like that. Right? You're not damaging the structural integrity of the muscle to any accelerated degree with BFR, but you can definitely tell something happened there. Now it's one of those things, hindsight, I wish we would have thought about it, because we did lactate measurements pre and post right before, and then as soon as we finished that 4th set, and then 2 minutes after release of the occlusion pressure, we did another lactate measurement as well. With half the work at that, as you would expect, right? Lactate takes a second to clear out of the limb, needs to circulate. Right. There's no significant difference between control and BFR at that 2 minutes release of occlusion. And that sounds like, well, that kind of goes against everything we think about with BFR, right? But it's with half the work.
Right.
Like half the number of repetitions, and you're producing the same amount of lactic acid. And so some of these other things, I mean, again, I'm not going to go into, I don't want to go into too much detail. I don't really know the numbers off the top of my head, but IL-6 was upregulated pretty significantly in BFR, but it was not in control. There was a difference between IL-6 and control. So, and that is a major inducer of satellite cell.
Yeah.
So to me, this is promising. So my next, I say, you can probably already guess where I'm kind of going with that, right? What happens if we make these kind of similar, right? What happens if we equate these loads and equate the number of repetitions, but keep this same protocol? Like what I did with this current JSCR study, but again, I'm kind of baby stepping here, right? I didn't want to just say, hey guys, you're being occluded for 2 sets, taking a break, right? I don't want to do that to them. So I'm kind of baby stepping into that. So that where we're at now.
Super fascinating. I mean, if you can get that at like half the reps, that's huge for maybe an older athlete or a guy like me who's like, I would much rather just do 4 squats than 12 to 14. That's pretty crazy.
Yeah, I mean, when I heard you say that, Lee, I just kind of wondered, do you potentially have like an exercise volume problem because you just haven't had enough reps at that load,
Yes.
We don't see that being the case. We can be the case when you do BFR with a light load. I mean, you can do just too few reps, but if you end up at fatigue, you get what you're looking for in fewer reps than if you were doing it free flow.
Exactly. And that's one of the major takeaways there, right? You do see, I mean, there definitely is a correlation between muscular fatigue during resistance exercise and trophic gain. There definitely is a correlation there. But that being said, right, it's one of those things, again, the data is not there. Like the IL-6 helps showing that we have same lactate with, half the number of repetitions performed. This is all suggesting, it's kind of as you said, right? We do have a volume issue, right? And that's because when designing this study, well, we had no idea how it was going to go, right? We were originally saying, okay, well, let's say we do 4 sets. We're telling everybody you're going to do 10 reps, 4 sets of 10 reps, right? Which is fairly standard at 75% of 1 RM. The control would have probably had no problem doing that.
Yeah.
But as the data suggests, it would have been way too much for BFR. So what would you do in that case? Then you would have had that volume issue immediately, right? Yeah. Where, okay, they couldn't reach that repetitions. They couldn't do that after set 2. And so that's a problem. And so we wound up going right till fatigue to see where that takes us, who performed more work. Obviously, we're all kind of expecting control is going to perform more work, right? That makes sense. And again, this is a huge case, right? So from here, looking at this and kind of the numbers that we had, we're going to go ahead and start cooking up another protocol where we are matching this and saying, hey, this is a rep range, and I'll pilot test it on myself. I'm like, I'm about to turn 37. If I'm 37 and can do this, a 21-year-old who's in good shape probably.
I'm honestly, if I'm being straight with you, I'm listening to this whole thing and I'm going, is there a way that we can limit who this podcast gets to? Because I'm afraid you're going to have a recruitment problem at some point.
Yeah. Well, hey man, just don't. I'll just tell all my students to stay away from it, right?
just throw some biopsies in as well. You're really just.
I've actually been working towards that. I've been training to do biopsies. Right now, it's just a matter of getting it approved by the university, which is It's a bit of an uphill battle, but I think eventually we'll get there. But that's one of those things. Definitely, most people hear that, and you show them kind of the procedure. No, it's something that's off-putting to a few people. So I'm kind of expecting that. But that's the route I eventually want to go, because just so much more you can tell. Again, if we're talking muscle damage, you're going to get so much more specific information from the actual muscle tissue itself. Now, granted, we have an ultrasound. We've been doing a lot of blood flow redistribution and blood flow evaluation with our ultrasound with BFR versus without BFR. We've been doing a lot of muscle swelling, basically musculoskeletal imaging to look at muscle cross-sectional area with our ultrasound. So you can still get some good data. We've already shown, and as expected, right? You're seeing muscle swelling with BFR where you don't see nearly as much with control, right?
Yeah.
That's kind of expected, and that's already been established because of metabolite accumulation, right? Translocating aquaporin receptors, you have greater osmotic draw. By default, it's going to happen. But the muscle biopsy would just be so great to be able to get that little bit of extra information, or lots of extra information that can directly just say, look, it is or is not causing damage in here to any significant degree or whatever.
What did you measure myoglobin in that last study?
In this last study, we are going to. We have not yet. It's been so funny enough. I am so used to basically these assay kits that I use, just standard ELISA assay or something like that. You order them, and literally 3 days later, if not less, I mean, it's basically like the Amazon Prime of the biologics world, right? Yeah. 2 days later, it's on your doorstep, right? Or the next day, I've actually ordered stuff at 5 p.m. and then had it the next day at 8 a.m. from Boston, right? And so we ordered them with about 3-4 weeks to spare before analysis. But the kit that I kind of know and love, I've used multiple times now, and I know it works, so I don't really want to deviate, was back ordered over and over and over again, and I never got it. So I went up,
COVID.
Yeah, man, it's COVID, I guarantee it. So we wound up going with a different assay. We went IL-6. We actually went with VEGF, vascular endothelial growth factor.
Yeah, good.
Analysis on that.
Oh boy, Dunkel's going to be happy. He's going to be so happy. One of our instructors, we call him Zach VEGF Dunkel.
Yeah.
Yeah. So he's going to just be so
Goes
giddy.
down every VEGF wormhole paper. Yeah. So yeah.
Nice.
Yeah. He'll be asking.
So yeah, we'll have a paper out there with VEGF to kind of add to that. Hopefully in the very near future. Like I said, they're currently in preparation, so hopefully those should be out. Depending on where, within 6 months.
Well, there was a rat paper that they did heavy load in rats on their plantar flexors with or without BFR, and at different occlusion pressures. And the higher occlusion pressure, they on biopsy, it really spared the muscle from damage. So the thoughts were, is there some weird like sparing of muscle if you were to do heavy load with BFR, a rat model, so take it for what it's worth. And then it was like, well, then you might have less volume per session, but you can do more sessions if the next day you're like, dude, I feel fine. Let's go again. So that's kind of what was interesting, is if you're going to see maybe there was some sparing of muscle damage or not.
Yeah, no, and that sounds pretty neat. Was it a longitudinal study or like a chronic training study, or was it just an acute?
It's been so long since I read it, Kyle. Do you remember? I thought it was an
acute study.
Just acute, yeah.
They measured mTOR. They measured muscle damage. They measured like force output. And they saw a fatigue kind of happen, trended really similarly to the control, but the muscle did fatigue more in the BFR group, if I remember correctly.
Yeah, for sure.
See, and I've always wondered, and that's one of the things that does kind of intrigue me about BFR is with BFR, especially if you're doing it for 8 minutes nonstop, right? Generally speaking, with resistance training, right, you have resistance training bout. You have your set, you have a rest period, 2-3 minutes where the muscle tends to recover, oxygen levels return fairly back to normal, metabolic accumulation is cleared, all of that, right? Versus, I do wonder, and I don't know how much it's been kind of looked at this point. I haven't dove too much into the research at this point, but as far as almost like an aerobic mimic, does it have any kind of effect there, right? Where if you keep it occluded, because a lot of these processes, like metabolic stress, for example, obviously we know it also stimulates mTOR. The metabolic stress does stimulate mTOR. However, it also stimulates like P38 MAP kinase and the AMPK signaling pathways that ultimately lead to enhanced mitochondrial biogenesis. So if you have enhanced mitochondrial biogenesis, you're talking about greater oxidative metabolism of the fibers. And I'm just kind of wondering, right? And that's another thing. Again, I'm always kind of coming up with new projects. I don't think I can feasibly do all the ones that I kind of like, man, that'd be so cool. But
well, that's always been the question, like, should you leave it on and just trap those metabolites for that extra minute? Just build it up like crazy. You've got this stuff in there that might be driving stuff like mTOR. Should we hold it? We know, especially with these Delphis, we can keep that damn stuff in there. Big time.
Oh yeah, absolutely.
It sucks, but yeah.
Well, and like I said, that's kind of evident in the lactate analysis that we did, right? I mean, it's just one of those Novo Biomedical finger stick lactates. But when you look at it, lactate immediately post-exercise without cuff deflation, so like cuff still on, inflated at 80%, lactate was up from like what baseline was about 1, give or take, immediately post-exercise after all these squats, it was like 4 or less, something like that. Then all of a sudden you deflate and way up, right? And that's what, and that just attests to the fact that you're not getting it. It's not circulating. It's not leaving. You're trapping it all there. Now, again, that comes back to, I wish we would have done a lactate analysis immediately after that second set, right? Because that's when we first initially deflated, cleared out all that lactate. I bet, and that's when they did the majority of the work, was there in that first set. I bet the lactate was through the roof. It's foolish. Now I'm going back and I'm correcting all this in this other study. I've already kind of got cooked up and started and all that. So that'll be interesting to see. So hopefully we can correct that.
Yeah, and it's fascinating. Lactate is a marker of moving into that fast twitch metabolism. So if you're seeing that, it just kind of drive up that's super cool. And so just to kind of put a bow on this, the protocol, the only thing different was that you had the cuffs on during the rest period for those first set rest period and then third set rest period. That was really the only thing different. Okay.
Well, no, it's one extra set and they were both till fatigue. Well, this one was 2 fatigue also. So it was one extra set till fatigue, still 75% of 1 RM. Yeah. So largely similar. We did a lot of additional, just because here. So this other one was performed at WKU, like as I was leaving, right? Okay. And so this one is performed here at Alabama, where I just have more equipment available. So we have a lot more pre-post analysis, but the protocol overall was the same. Yes. So we have a lot more functional data to go along with that protocol now. So you can get a lot more, obviously as a result, we get a lot more information. So
yeah, cool. Well, anytime we see IL-6, I mean, that makes everyone's ears perk up. That's just a driver of all things good. And we haven't seen that enough in the BFR literature, I don't think. There is some.
I agree.
Yeah,
I agree. And that's kind of just with everything we found out that it's involved with, right? Back in the day, I mean, when you thought IL-6, everybody was like, oh, it's pro-inflammatory, right? It's a pro-inflammatory cytokine. Come to find out, if it's released from the skeletal muscle, it's largely anti-inflammatory and helps protect the muscle and helps stimulate growth and repair. Conversely, if it's released from your mononuclear cells, right, your neutrophils, monocytes, macrophages, whatever, that it's almost always pro-inflammatory and has a pro-inflammatory effect. So kind of interesting, right?
Yeah. What about any other new and cool projects you want to tease right now, or?
Yeah. So like I said, we did do, man, I've got a bunch. So I have,
Lee, we've only got today. We can't. Just...
I'll keep it slow, man. I'll keep it simple. But no, I've got
Yo, Johnny asked, "You got any more project?" Lee's like, "Roll Tide, I sure do."
Let's go.
Roll Tide, man. And hey, Kyle, you even added in the accent, man.
Hey, I got the accent, Lee. Oh yeah, I can add it, baby.
That was something. I was like, I feel like I'm kind of starting to develop on some words like that, a Alabama accent. Like at first, I started saying "Roll Tide" as kind of a joke, And now I find in general conversation, if I say Roll Tide, it almost always has that little bit of a little bit of an accent to it. I'm like, oh man, what am I doing?
They put something in the water. It makes you have to do that.
Hey, it's all right. Man, I will say the football games here are infectious. If you ever, I'll be honest, I was so anti-Alabama before I got this job. I mean, I went to a Big Ten school. I went to Purdue, and it was right after Drew Brees was there. So at the time,
nice, yeah.
And then obviously we all know what they tanked. I still love Purdue. They're just not the same as they used to be as far as football prowess. But went to Louisville. Louisville at the time was in the Big East. Eventually wound up in the ACC. They had Teddy Bridgewater during my time there. Right, they were actually really good. That was when we had Charlie Strong, and so I've always been a big football fan. And then, man, when I got the job off here, I was like, man, I don't know if I could ever root for Alabama. I got to my first Alabama football game. I kid you not, man. I don't know. Have either of you been to one?
I've been in the stadium and the athletic department, but I've never been there during football season.
Man, I swear. So first game I went to was, I think it was, if I recall, it was like New Mexico State versus Alabama at Alabama. One, you'd be like, okay, if it was Purdue, there would have been like 15 fans in the stadium, right? Yeah. I came to this first game, not to knock Purdue again. I love Purdue. Don't get me wrong. That's where my heart lies there. But man, I went in there and you would have thought it was like, if you're comparing to the Big Ten, you would have thought it was Michigan, Ohio State. You'd have thought it was the biggest game of the year or something like that, man. It was absolutely nuts. And so after the first game, I was like, all time. It was one game, man. It was nice.
The athletic department's all trained. They have a lot of Delphi units. So the stuff you're doing, not that Alabama and Saban needs any extra help with these badass strengthening protocols you're looking at. Yeah. But I in all seriousness, man, they should get in touch with you and start seeing what you're doing, because I know they do look at ways to use this in the weight room as well. Yeah,
well, I would say one cool thing, and I think and this is, I'm no one to give advice on Alabama football, but I do think that is cool. Is a lot of people were worried when Scott Cochran left, our strength coach, and we wound up getting our new strength coach team. One of which is his name's Matt Ray. He's actually an exercise physiologist. Used to be an exercise phys professor, and you should see the analyses he's running on his plays. It's amazing. It's like everything you learn as an exercise physiologist, you're like, why are we not using this? But he's using it all, and it's awesome. I'm like, because I went over there, I met the guy a few times, nice guy, and just seeing him integrate all this, I'm like, that is so cool, like so great, like using force transducers and things like that to measure. Just everything. Like it's so cool. I like it. I was geeking out when I was over there. So yeah,
great. That's all we need is freaking Alabama to keep winning. I'm a little bit done with it, man.
Yeah.
Hey, man, I will say this, for me, that's job security. Right?
Yeah.
Our campus size is, like, if I'm not mistaken, doubled in the last 15 years. And clearly that has some correlation. It may not even been 15, but clearly there's some correlation there with Nick Saban's arrival. And as a result,
that's nuts.
Yeah, that our program, our exercise science program, I think we're around, and don't quote me on this, but I think we're around 900 undergrads in exercise science. And so as a result, I got hired, right? They were looking, and they had a job opening. So I'm like, man, keep winning, Alabama.
Yep.
For me, man.
Everybody likes a winner.
Exactly. But yeah.
So what do any of your other stuff that you just kind of want to tease?
Oh yeah. So I was saying it's, I think more of kind of like an applied thing for your average gym rat. So we were doing, obviously we're using our Delphi more as like kind of the standardized, right? Kind of like the norm, what we know is going to happen for lower limb occlusion. We started messing with those tissue wraps, those band wraps, like Rogue makes, like Voodoo and such, kind of messing with those and looking at alterations to fatigue. I have a project where I'm currently, very slowly, but currently working on the manuscript for, where similar type of protocol, 5 sets of 5 knee extensions and flexions at maximal on a isokinetic dynamometer. I don't know if you know the HUMAC or not, but
sure.
Right. So HUMAC, and I'm doing it, comparing it to a physiological constrictor. So looking at ice. So ice is a physiological constrictor and seeing kind of how that works. But it's, I say for benefit to Owens Recovery Science, there's a marked difference between BFR and ice. Like BFR just induces fatigue. You see strength plummet again. Like by end of that 5th set, 5 sets of 5 repetitions, that 25th rep, you're barely moving your leg.
Yeah.
So you're just kind of hoping it fully extends, right? So those are some projects we're looking at. We've got some stuff looking at upper body blood flow redistribution with BFR. And that's the reason why Ray Van Wy, right, who we both know, he and I are working on a manuscript together. And like I said, I'm integrating some stuff about a pressor reflex in there. And that kind of comes along with the research that I'm currently doing. And then trying to think, another study is that I think you'll probably like. It's right, as opposed to, so how we have alteration where we can do 10%, 20%, 30% of limb occlusion pressure right off that personalized tourniquet pressure. We're actually matching and seeing how much is that actually occluding blood flow. So if you're about 80%, is it actually occluding 80%? And so, and that's where it kind of comes to where I had mentioned during that study, some of this shows, and this is where another project of mine is going. I already have the IRB kind of in progress, where 60% and 80% really are not that different as far as, this is after like 30 something people doing this analysis, seeing what their blood flow is reduced by as far as percent of original blood flow in their posterior tibial artery. And as a result, like 60% really is not that much different. And so for me, I'm wondering, right, not necessarily at low intensity. Low intensity, I think you need all the occlusion you can get to really drive hypoxia. But if you're talking about exercise tolerance at these higher loads for what I'm doing, 60% discomfort versus 80% discomfort could be a major help with being able to complete more reps and get more work in to have some of these effects going on. So that's kind of where I'm going, but it's kind of a cool study. So we did every percentage by 10 from 0 to 100 to check how blood flow is changing. So it's going to be, hopefully that's going to be a good paper. That one's already kind of in development. So
we've put that out in a paper as well. And we're starting to see it, the heavier the load, the more we think you should drop. The lower the load, the more we think the hypoxia is what you need. Now it's even like, okay, we're looking at 100% limb occlusion. If you're almost at no load, potentially induce this cell swelling, or if you're just using something like E-stim. And so on that, I know you and I talked about this. I remember at Louisville, you discussed in your paper, other drivers of maybe this anabolic response with BFR. One is potentially the cell swelling. What are your thoughts on that, and how important you think it might be to what we're seeing with BFR?
Yeah, I think cell swelling is important. I think it's another mechanism. Obviously, it's tied to metabolic stress, right? The reason we see cell swelling is largely because of osmotic draw due to the production of metabolites. It's causing water to be drawn into the cell. Well, it's just like, similar but different to mechanotransduction. Whenever you cause that cell swelling, you're putting extension on that cell membrane, on the sarcolemma, right? And as a result, that's activating integrin receptors that are going to ultimately drive adaptation. And so I think that's definitely important. I think that's going to be a fact that you definitely don't want to take away. If you can, the way I've always thought about this, and I could be wrong, but at least this is what's driving the majority of my research, is if you have X, Y, and Z things that are driving hypertrophy, why take away one of them, right? Or if you have the ability to add them, why not add them, right? At least then, even if it's not going to make it any higher than it would have been with extensive resistance training, maybe you achieve that hypertrophy more easily, right? That's at least at the bare minimum. But I still have my faith in it, that I think we're going to see some pretty profound stuff with BFR high intensity. I really do. It's based on the preliminary stuff that we're seeing. I think there's some definite logic to why we could see synergistic adaptation to have greater than, or super physiological hypertrophy than compared to what you would normally see under high loads. And
if cell swelling is a thing, the way sounds like you really drove up lactate with very few reps in that BFR group is pretty fascinating.
I think those last 2 sets combined was about 10 reps.
Wow.
Between 2 sets at 75% of 1 RM. It may have been less if I recall. So yeah, it's not a lot of work to drive up that lactate, right?
Yeah.
It's
my kind of workout, man. Not a lot of work guy.
But yeah, and that's what I say. If 60% can do the same thing, but not people be like, this is uncomfortable, man. Like, okay, I get it. That's fair. Let's go that route if we can. So that's what I'm going to start exploring. So
well, this is badass stuff. And again, thanks for your work, because it'll help us, because we get this question all the time of how we should be doing this in the gym, with the teams that we work with. So let's share the next results with the University of Texas first, before we let Saban get any more good data from you. So cool, Lee.
Oh, man.
Thanks for your time, brother.
Definitely. It was good talking with you guys.
Roll Tide, man.
Roll Tide.
Thanks for listening to the Owens Recovery Science Podcast. Owens Recovery Science is a single source for PTs, OTs, ATCs, DCs, MDs, and other medical professionals seeking certification in personalized blood flow restriction rehabilitation training. Find them online at owensrecoveryscience.com.